Good day. In this video, we are going to talk about curve tracing and apply the concept of derivatives in order to provide more information about curves or graphs in general. So when we say curve tracing, we usually think of point plotting. This is done by defining points or ordered pairs and just plotting the points. Say for example, we are given y equal to x squared minus 1. What we want to do first is to assign x values, or just choose any x values and then solve for the corresponding y values so we can obtain the ordered pairs or the points. Now what we need to do next is to plot the points. So we have -1, 0, we have 0, -1, so 0, -1, and then 1, 0, so 1, 0. Lastly, we just connect the points. So that's simple point plotting. This is done just to give a rough sketch of the graph of a function. Now, what we want to do is to extract more information, important information or details about a graph that simple point plotting cannot give us. So let's talk about some important properties or characteristics of general curves. You have the domain, intercepts, and symmetry. These three are the non-calculus portion. Then you have the calculus portion, asymptotes, critical points, monotonicity, and local extrema, and lastly, inflection points and concavity. So let's go through each of them by having an example. Let's say we are given y equal to x cubed minus 3x minus 2, and we are asked to provide the information stated earlier from the domain up to the concavity, and then ultimately sketch the graph. So let's start with the domain. Recall that the domain is the set of all x values that will make the function defined. So we have to avoid undefined and imaginary function values. So in this case, it will not result to division by 0 or an even root of a negative number. Therefore, we can say that the domain is the set of all real numbers. Next, let's solve for the intercepts. Recall that these are points where the curve crosses the x-axis if it's the x-intercept, or the y-axis if it's the y-intercept. So if we want to solve for, say for example, y-intercept, you have to equate x to 0 and then plug in x equals 0 to the original function. So plug in x equals 0, we get y equal to -2, therefore the y-intercept is 0, -2. Solving for the x-intercept, you have to equate y to 0, so plugging in y equals 0, we get this equation, 0 equal to x cubed minus 3x minus 2. In order to solve for the x value or values, we need to factor. So these are the factors, and then we apply the zero factor property where we equate all the factors to 0. So we have x minus 2 equals 0, and then x plus 1 squared equals 0. So we have two x values, x equal to 2 and x equal to -1. Therefore, we also have two x-intercepts. So 2, 0 and -1, 0. So these are the intercepts. Next, let's find out if there is symmetry in the graph of the function. This has something to do with mirror images. Okay, we have symmetry with respect to the x-axis, symmetry with respect to the y-axis, and symmetry with respect to the origin. If a graph of a function is symmetric, for example, with respect to the x-axis, then whatever is below the x-axis, if a curve is present below the x-axis, then a mirror image of this curve is present on or above the x-axis. Okay. Let's say your graph is symmetric with respect to the y-axis. So this is the y-axis. If a curve is present on the right side, then a mirror image is also present on the left side. Okay. For symmetry with respect to the origin, the mirror images are diagonal with each other. Okay. Say for example, a curve is present on the first quadrant, then its mirror image is located on the third quadrant. So this is symmetry with respect to the origin. Or if the curve is present on the second quadrant, then its mirror image can be seen in the fourth quadrant. So this is again symmetry with respect to the origin. Okay. So to determine if there's symmetry, say with respect to the x-axis, what we need to do is to replace y with negative y and check if the resulting function is the same as the original function. In other words, if we replace y with negative y, if the function is unchanged, then we have symmetry with respect to the x-axis. So initially we have y equal to x cubed minus 3x minus 2. Replacing y with negative y will result to this equation. If we compare this to the original equation, obviously it's different. Therefore, we can say that it's not symmetric with respect to the x-axis. Let's check if it's symmetric with respect to the y-axis this time. So instead of y equal to negative y, this time we replace x with negative x. Okay. So initially, this is our function. Plug in negative x for x will result to this equation. Y equal to negative x cubed plus 3x minus 2. It's still different from the original function. Therefore, it's not symmetric with respect to the y-axis. Lastly, let's test if it's symmetric with respect to the origin. So for the origin, we have to simultaneously replace y with negative y and x with negative x. So plug in negative y and negative x, we'll get this equation. Negative y equal to negative x cubed plus 3x minus 2. Let's try if we multiply both sides by negative 1. Let's see if it will result to the original equation. So we have y equal to x cubed minus 3x plus 2. So it's still different, therefore it's not symmetric with respect to the origin. In conclusion, we don't have symmetry for this particular function. Next, let's solve for the asymptotes. Remember that asymptotes occur if we have a rational function. In other words, a polynomial over a polynomial. However, for this particular function, we only have a simple polynomial function. Therefore, we can immediately say that there are no asymptotes. Okay. The next, we'll solve for the critical points. These are points that indicate a change in the behavior of the graph of a function. Let's say from increasing to decreasing, so on and so forth. So how to find the critical points? We first need to differentiate our function. So from y equal to x cubed minus 3x minus 2, we take the first derivative, y prime equal to 3x squared minus 3. And at critical points, the slope of the function is horizontal. If the slope of the function is horizontal, therefore the value of the slope is 0. Okay, so we equate this equation to 0. and then we solve for x in order to get the critical value, the critical x value. Okay, so we can take out 3 or factor out 3 so that we are left with 0 equal to x squared minus 1, and then solving for x we get x equal to positive and negative 1. So these are the critical values. And since we are after critical points, we need to get the y values also. Okay, so solving for the y values at x equal to 1, just plug in x equal to 1 to the original equation. So we get y equal to negative 4 at x equal to 1. Therefore, one of the critical points is 1, negative 4. And then at x equal to negative 1, plug in x equal to negative 1 to the original function. We get y equal to 0. So this is the second critical point. Next, let's find out at what interval or intervals the graph of the function is increasing or decreasing. And then using the first derivative test, let's find out whether the critical points that we obtained here is a relative maximum or a relative minimum. So we'll test for monotonic functions and local extrema using a sign chart, because we want to determine the sign of the first derivative. From the sign of the first derivative, we can conclude whether it's increasing or decreasing for a particular interval. So let's start with the intervals. This is based on the critical values. Remember that we obtained x equal to positive and negative 1 as the critical values earlier. These values divide the rectangular plane into regions. Okay, so let's say this is negative 1, this is positive 1. So these are the regions. We have negative infinity to negative 1, negative 1 to positive 1, and then positive 1 to positive infinity. We just list down these intervals in the first column. Next is to choose any x value within the intervals. So let's call them test values. Okay, for the first one, negative infinity to negative 1, just choose any test value or just choose any x value within the interval. Let's say we use negative 2. Okay, then negative 1 to 1, we can use 0. Then lastly, for 1 to infinity, we can use 2. Next is to determine the sign of the first derivative by plugging in the test values to the equation of the first derivative. So if we plug in negative 2 to y prime equal to 3x squared minus 3, we'll get a positive value. If we plug in 0, we'll get a negative value, and then if we plug in positive 2, we'll get a positive value for the y prime. Okay, again, the sign of the y prime will dictate if it's increasing or decreasing. Okay, so let's call this column the trend or the behavior of the curve for a particular interval. So first one, y prime is positive, therefore it's increasing. If it's negative, then it's decreasing. Again, if positive, increasing. Lastly, we test if the critical point is a relative maximum or a relative minimum by looking at the change in the trend of the curve from one interval to another. Okay, so first one, there is a change from increasing to decreasing. So the graph is going upwards from left to right on the first interval, and then going downwards from left to right on the second interval. Again, change from increasing to decreasing. Therefore, at x equal to negative 1, we have a relative maximum. Okay, and then for the next two intervals, again, the middle interval or middle region, the graph is decreasing, and then for the rightmost region, the graph is increasing. Therefore, at x equal to 1, the graph has a relative minimum. Next, let's talk about inflection points and concavity. For concavity, you can think of it as the opening of the curve, whether it's opening upward or opening downward. Inflection points, on the other hand, these are points where the sense of concavity changes. Let's say on the left side of the inflection point, the concavity is upwards, and then on the right side of the inflection point, the concavity is downward. So as long as there is a change in the sense of the concavity, then we have an inflection point in the middle. Okay, so we'll make another sign chart later on. First, let's solve for the inflection points. Initially, this is our function. To solve for the inflection points, we need to equate the second derivative of this function to 0. So this is the first derivative, this is the second derivative. Equating this to 0 and then solving for x, we get x equal to 0. If x is equal to 0, then y is equal to negative 2. Then this point is a possible inflection point. We don't know yet if this is indeed an inflection point, so we need to verify first using the second derivative test. Okay, so let's make another sign chart for the second derivative test. Start again with intervals. This time, instead of using the critical values or the x value of the critical points, we'll be using this time the x value of the possible inflection point. So we have x equal to 0. Then this is our x-axis. Let's say this is x is equal to 0. So we have two regions. Okay, negative infinity to 0. And then 0 to positive infinity. Okay, so list down the intervals in the first column and then choose any x value within the interval. For the first one, negative infinity to 0, we can use negative 1. And then for 0 to positive infinity, we can use positive 1. Next is to determine the sign of the second derivative. So plug in negative 1 to the equation of the second derivative. So y double prime equal to 6x, where x is equal to negative 1. So we get a negative value. If x is equal to 1, then we get a positive value. Next, based on the sign of the second derivative, we can conclude whether it's concave downward or upward. If the sign is negative, then it's concave downward. We can just draw a downward arrow symbol. And then if your y double prime is positive, then it's concave upward. Okay, so test for the inflection point. Again, we just want to know if there is a change in the sense of concavity, and obviously for this particular function, there is a change from concave downward to concave upward, from left to right. Therefore, at x equal to 0, we have an inflection point. So now let's summarize the important points. You have the intercepts, you have the critical points, and you have the inflection point. And then we have the sign chart for the first derivative test, the sign chart for the second derivative test. We are now ready to sketch the graph of the function. Okay. So before we sketch the graph, let us look at how a curve behaves if we combine the concept of monotonic functions and concavity. So for monotonic functions, you have two types, increasing and decreasing. For concavity, we also have two types, concave upward and concave downward. So let's look at the pattern that a curve follows if we combine these two concepts. So say this is the trend, concavity. So for the trend, we have increasing, then decreasing. If an increasing function is combined with a downwards concavity, then it looks something like this one. So the graph will look something like this one. So increasing, it goes upwards from left to right, but the concavity is downwards. Okay, and then increasing coupled with an upward concavity, then it's still going upwards from left to right. However, the concavity is upwards. Okay, so if the function is decreasing and then the concavity is downwards, so decreasing meaning the graph is going downwards from left to right, and then the concavity is downwards also, then it looks something like this one. Okay, and then again, if decreasing, however, if the concavity is upwards, then it looks something like this one. Okay, so let's apply these patterns in sketching the curve. Okay, let's start by plotting the important points. Let's start with the intercepts. 0, -2. Then we have -1, 0, 2, 0. So these are the intercepts. Next, we have the critical points. -1, 0. Remember, this is also one of the intercepts. So this one, -1, 0. So label that as the critical point. And then another critical point, +1, -4. This one. So this is another critical point. Okay. So if we go back to the sign chart of the first derivative test, we determined that at x equal to -1, we have a relative maximum. So this is the highest point in this interval. Okay. And then at x equal to +1, this point, this is a relative minimum. So this is the lowest point in this interval. Okay. So let's start connecting the points. Let's do this one interval at a time. Okay. So let's start with this interval, -∞ to -1. If you notice, this interval, -∞ to -1, is under this interval, -∞ to 0. So this one is -∞ to 0. Inside -∞ to 0, we have the interval -∞ to -1. The trend is increasing at this point, at this interval, and then the concavity is downwards. So increasing downwards, increasing downwards, the graph will look like this one. Okay. Next interval is -1 to +1. At this interval, the graph is decreasing. So from -1 to +1, the graph is decreasing, meaning going downwards from left to right. However, the concavity changes from downwards to upwards because we have an inflection point. Okay, so first one, decreasing and then downwards. So decreasing downwards, the graph will look like this one. So decreasing downwards, right? And then the same trend, decreasing, but this time because we have an inflection point, the concavity changes from downward to upwards. So decreasing, but with the concavity of upwards. So decreasing upwards, so the graph will look like this one. Okay. And then lastly, from +1 to infinity, so +1 to infinity, the graph is increasing. Okay. And then the concavity is upwards. So increasing upwards, the pattern is like this one. Okay. So this is now our graph. If we use a graphing tool, then the graph will look like